In this next series of videos, I want to cover the topic of the step response of networks. These are related to the frequency response, but they are functions of time rather than functions of frequency. It turns out that there are some very simple relationships between the frequency response of a network and its time response in this particular case, and we'll be exploring some of those as we go through. In this first video, I just want to take some time to define what I mean by a step response and introduce the order of response, something which I think I've mentioned earlier but have never fully defined. And then we'll have a look at the simulator and the two different ways of simulating step responses in the simulator. So, firstly, what is a step response? Well, a step response is the response of a circuit, in other words, its output, when its input is a step. And unless we specifically say otherwise, which we very rarely do, when we say a step input, what we mean is a unit step. And a unit step is a waveform that is 0 for all time up until t equals 0, and then it jumps up to 1, and it remains at 1 for all time from then on. Since the input has been 0 for all time until the step arrives, we can assume that all capacitors in the circuit are fully discharged and that there are no currents or voltages anywhere in the circuit. However, as soon as the step arrives, currents will start to flow, voltages will start to move above 0, and in some cases below 0, and the output of the circuit will no longer be at 0. We will have what is described as a step response. We've seen a couple of simple cases of this already. If you consider the circuit that we looked at previously when we were thinking about charging up capacitors, you had a circuit like this with a voltage source here, and I think there was a switch there which we closed at time t equals 0. Well, having a 1 volt source here with a switch that is closed at time t equals 0 is exactly the same thing as putting in, to this point in the circuit here, a unit step. Since before the step arrives, all the voltages and currents in the circuit are 0, as soon as the step arrives, some current starts flowing through the resistor, charging up the capacitor, and the voltage on the capacitor starts to increase. So if we were to plot the voltage at this point here, I'll call it A, we might get something like this. Shoots up to 1 volt at time t equals 0. And if we were to plot the voltage at point B in the circuit, which would be the output that we're interested in, then as we've seen before, the result is we get this exponential rising shape that never quite gets up to 1 volt. And this is a step response. It's a response of the circuit to an input step. Another way to analyse these circuits is in the frequency domain, in terms of their frequency response. And we can easily work out the frequency response of this circuit. Just h of omega is, using the potential divider formula, 1 over j omega c over 1 over j omega c plus r, multiply up by j omega c to get a polynomial on the top and the bottom, and we just end up with 1 over 1 plus j omega rc. We can see that in this frequency response there are no zeros, i.e. there are no values of j omega for which the numerator is 0, but there is one pole. There is one value of j omega for which the denominator is equal to 0. So we would call this a first order circuit, and we would refer to this step response as a first order step response. The order is given by the number of poles in the frequency response. And since a polynomial with a maximum power of its variable of n has n roots, you can also think of the order as the maximum power of j omega that appears in the denominator. When we're simulating step responses using the simulator, there are two different ways that we can get the step response. The first is to do a transient simulation. We've seen these kind of things before. Have a DC source here, feeding this capacitor through this resistor. So we would expect a step response like this, the exponential rise. And this happens because the simulator assumes that when you're doing a transient response, any DC voltage source like this has a value of 0 until time t equals 0, and then it takes its value of, in this case, 1 volt. Otherwise, the output transient response wouldn't be very interesting. It might be clearer if I add another a voltmeter to this circuit. Right, now if I do a transient response, you'll see that the input voltage remains at 0 and then shoots up to 1 volt at time t equals 0. That's indicated by this little diamond here, that's time t equals 0. And the output, which is the blue trace here, measured by this voltmeter, that is the step response. It is the output when the input is a step. Now, that is one way to get the step response out of the simulator, but it's not the quickest way. The quickest way is to determine it from doing a frequency response measurement. I mentioned before that there is a close relationship between the frequency response and the step response of a network, and you can in fact derive the step response from the frequency response. To get a frequency response, of course, we can't use a DC source like this anymore. We'd have to replace that DC source with an AC voltage source. And we no longer want to do a transient simulator. We want to do a frequency response measurement, and you'll see that this system, we don't need that voltmeter anymore either. This network here has a frequency response given by the one pole shape, which hopefully we're getting quite familiar with. It stays horizontal until around the break frequency, and then it heads down at 20 dBs per decade. You can also press the step response button, and it will plot the step response of this network. Now, this changes the time scale. So you see, if I get the time scale at an appropriate value, you've got this exponential rise again. And what's happening is the simulator is calculating the step response from the frequency response. And once you know how to do it, that's a much faster way to determine the step response of the network. That's all I want to say this time. Next time, I'll consider a little bit more about step responses in real life.